Hi everybody, in this video we're going to talk about prime and composite numbers. So let's start off by talking about what a factor is, because this is part of the definition of what a prime or composite number is. So a factor is basically something that divides the number you're talking about. Or you can also think about it as a number that you could write a multiplication fact with to get the number you're talking about. So, for example, the number 12 has 1, 2, 3, 4, 6, and 12 as its factors, because those are the numbers that evenly divide 12, or the numbers that you can put in pairs and multiply together to get the number 12. So that's the definition of a factor. And the definition of a prime number is a counting number that has exactly two factors. And then a composite number is a counting number with more than two factors. So one way that you can visualize this is that prime numbers can only form rectangular arrays that have one row. But composite numbers can form rectangular arrays that have one row or more than one row. So there's multiple ways that you could arrange that number of squares into a rectangle. And sometimes there's even more than just one that has more than one row. Like, for example, if you had the number 24, the number 24 could be arranged in a rectangular array of 3 by 8 or 4 by 6 or 2 by 12 because it has lots of factors. So that's what a prime number is versus a composite number. And one way you can think about it is that a prime number is a number that can only be divided by one in itself. So one of the ways that we can find a list of prime numbers is to use a process called the sieve of Eratosthenes. I think that's how you say it, but I also don't speak Greek. So basically the way that this process works is you identify prime numbers and then you look for the multiples of those prime numbers. So to start off with this process, we'll look at the smallest number, which is the number 1. And this number is not prime and it's also not composite because a prime number has exactly two factors and a composite has more than two factors. And the number 1 only has one factor because the only number that divides it evenly is the number 1. And so 1 is neither prime nor composite. But if we go on to the next number, which is the number 2, this number is a prime number because it only has two factors. It has the factor 1 and the factor 2. And so what I'm going to do is, since this is a prime number, I'm going to cross off any multiples of that number because, say, for example, the number 4, this is not going to be a prime number because the number 4 can be divided by 4 and 1. And any number can always be divided by itself and the number 1. But since it's a multiple of 2, it can also be divided by 2, which means that it's a composite number because it has more than two factors. So I'm going to cross off all of the multiples of 2 because all of these numbers will be composite numbers. So now that I have all the multiples of 2 crossed off, I'm going to move on to the number 3. And the number 3 is guaranteed to be a prime number because it wasn't crossed off, which means it doesn't have any factors that are smaller than it, aside from the number 1, because every number has 1 as a factor. So the number 3 is a prime number, and now I'm going to go through and cross off all of the multiples of 3. So 6 is already crossed off, but I'm just going to go ahead and cross it off anyway so that I can see the pattern more clearly. Then I have 9, and basically I'm just going to go through and skip count by 3s and cross off all the multiples of 3. So as I do this, I'm eliminating all of the composite numbers that are divisible by 3. All right, so now we have all of the multiples of 3 crossed off. So I'm going to move on and cross off all the multiples of 5. So I'll say, okay, well, the multiples of 5 are numbers that end in either 0 or 5. So that actually makes it really easy to cross out because of the way that this list of numbers was arranged. So I'll just cross off all the numbers that end in a 0 or a 5. And that gets me to there. And then I'll move on to my next prime number, which is a 7. And there's actually a shortcut once you get up into some bigger numbers. because the number 7, when I'm looking for multiples of 7 to cross off, I don't need to look for 1 times 7 or 2 times 7 or 3 times 7 or 4 or 5 or 6 times 7, because all of those multiples have already been crossed off. Because when I crossed off all the multiples of 2, that also crossed off all the multiples of 4 and 6, because 4 and 6 are divisible by 2, which means that their multiples are also divisible by 2 and they were already crossed off. And so since I crossed off all the multiples of 2, which includes the multiples of 4 and 6, as well as the multiples of 3 and 5, that means that I've already crossed off 7 times 2, 7 times 3, 7 times 4, 7 times 5, and 7 times 6. And so that means that the first number I need to check to see if it's crossed off is 7 times 7, which is 49. So I'm going to go ahead and cross that one off, and then I'll check all of the multiples above that. So 7 times 8 is already crossed off because 8 is divisible by 2. 7 times 9 is also already crossed off because 9 is divisible by 3. And 7 times 10 is already crossed off because 10 is divisible by 5 and 2. So all of those are already crossed off, but 7 times 11 is not crossed off yet because 11 is not divisible by any of the numbers that I've already checked. And so I'll cross off 77, and then 7 times 12 is 84, but that one's already crossed off because that's a multiple of 2. And then there are no other multiples of 7 that are on this list, and so I'm good with the multiples of 7. Then we can go through and do the same thing for the number 11. So again, we don't need to check 11 times 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10 because all of those multiples have already been crossed off. And so the first one I need to think about is 11 times 11, which is actually off of this chart that I've drawn here. And so that means that I don't have any multiples of 11 that are within the number range that I'm looking at. Obviously, if you had a longer list of numbers, then you would. But in this case, since 11 times 11 is 121 and my number chart only goes up to 90, that means there are no multiples of 11 on this chart that need to be checked. Then you would go through and say, okay, well, that means that 13 is a prime number because it hasn't been eliminated as a multiple yet. And 13 squared is also bigger than 90, so there are no numbers that I need to cross off in this list that are multiples of 13. And basically with the same reasoning, you'll find that all of these numbers that have not already been crossed off are prime numbers. And basically, like if you had a really long list of numbers, you would need to keep going through and checking for multiples. Or if you had an infinitely long list of numbers, you would also need to do that. But in this case, basically all of these circled numbers are the numbers from 1 to 90 that are prime numbers. And the prime numbers that we'll be using the most in this class are the small ones, like the number 2, 3, 5, 7, 11, and so on. But it is important to know that there are big prime numbers like 59, because there are no other numbers that divide 59 besides 1 in itself. So one of the defining characteristics of prime numbers and composite numbers is that every composite number can always be expressed as a unique product of prime numbers. So the word product means multiplication or the result of multiplication. And what this means is that any composite number can be broken down into a series of prime numbers that are multiplied together. And the way that we figure out what those prime numbers are is through a process called prime factorization. So the way that prime factorization works is you take your composite number and you break it up into 2 factors. And it doesn't matter which 2 factors you choose as long as they multiply together to 24. So I might say, okay, well, because 24 is an even number, I know that it's divisible by 2, and 2 times 12 equals 24. And if either one of your numbers is a prime number, then the process ends there. So the number 2 is a prime number, so I'm going to circle it because I can't break down the number 2 into more factors that are unique or helpful, because the only numbers that divide 2 evenly are the numbers 1 in itself. But I already have the factor 2, and you could have an infinite number of 1s and multiply by them, and it still wouldn't make any difference. So I'm just going to circle the number 2 since it's prime. But the number 12 is not prime, so I'm going to break that one down further. And 12 is also an even number, so I'll divide by 2, and that gives me 6. And 2 is a prime number, but 6 is not, because 6 can be broken down into 2 times 3. And in this case, both of the factors that I broke it down into are prime numbers. And so that means that I'm done with the prime factorization. And so the product of prime numbers that 24 is equal to is 2 times 2 times 2 times 3. And it doesn't matter how you do your factor tree, you'll still get the same result in any case. So for example, another way that I could have broken up the number 24 is I could say, well, I know that 3 times 8 equals 24. And 3 is a prime number, and 8 can be broken down into 2 times 4. 2 is a prime number. 4 can be broken into 2 times 2, and those are both prime numbers. But notice that the prime factorization is still the same. We still have 1, 2, 3 2's multiplied together. So we'd have 2 times 2 times 2 times 3. So the prime factorization looks the exact same regardless of how you choose to set up your factor tree. As one more example of what this could look like, you could say 24 equals 4 times 6. So you could do 4 times 6. Neither one of those is prime, so I need to break them both down further. The number 4 can be broken down into 2 times 2, which are both prime. And 6 can be broken into 2 times 3, which are also both prime. But again, notice that the prime factorization ends up being the exact same because you have 3 2's and 1 3 that are all multiplied together. So that's how you can find the product of prime numbers that a composite number is equal to. And that's called prime factorization. And then the last thing I want to talk about is the prime factor test. So the prime factor test says that when you're testing for the prime factors of a number n, you only need to test the prime numbers where the prime numbers are less than or equal to the square root of n. So for example, if I was trying to find the prime factors of the number 161, the square root of 161 is approximately 12.68, etc. And the prime numbers that are less than that are the numbers 2, 3, 5, 7, and 11. And so these are the prime numbers that I need to check to see if 161 is divisible by them. And this kind of goes back to what we were talking about with the sieve of Eratosthenes, where you only needed to check after the number squared. So like when we were checking the multiples of 7, we started at 7 squared because 7 times all of the numbers less than 7 were already crossed off in the sieve of Eratosthenes. So this is kind of the same idea, but it's just using the result in reverse, if that makes sense. So I'm going to go through and test all of the prime numbers 2, 3, 5, 7, and 11. So for the number 2, I can use the divisibility test, and I check the last digit. And since the last digit is not even, that means that it's not divisible by 2. To test if it's divisible by 3, I can add up all of my digits. So 1 plus 6 plus 1 is 8. 8 is not divisible by 3, so that means 161 will also not be divisible by 3. The number 5, the multiples of 5 either end in 0 or 5, which in this case, this number doesn't, so it's not divisible by 5. And for the number 7, that one doesn't have a divisibility trick, so let's do 161 divided by 7 on my calculator. And in this case, it does divide evenly because 161 divided by 7 equals 23. And so this would factor into 7 times 23. 7 is a prime number. And then the number 23 also happens to be a prime number because if I apply the same prime factor test to this number, 23, if I take the square root of 23, that's going to be 4 point something. Because it's pretty close to 25 and the square root of 25 is 5. So the prime numbers that I need to check are the prime numbers that are less than or equal to 4 point whatever that decimal is. So those prime numbers will be the numbers 2 and 3. And 23 is not divisible by 2 because it doesn't end in an even number. And it's also not divisible by 3 because 2 plus 3 is 5, and 5 is not divisible by 3. And so that means that this is also a prime number. And so notice that the number 161 did have a factor that was greater than its square root, but you were able to find that prime factor by checking the prime factors that were less than that square root. And so that's how the prime factor test works. And you can apply the prime factor test as many times as you need to until you get the prime factorization of the number. So that's how prime and composite numbers work. If you have any questions, let me know. And I hope you guys have a great day.